Hello and welcome to Set Theory, a bite-sized lecture series. In these videos, you'll get a conceptual overview of set theory that doesn't take all day. If you're new to this channel, be sure to check out the playlist with all the videos in this series, which I'll link to in a card in the corner of the screen. Last week, we learned about relations. If you haven't watched that video, you should definitely go do that now. I'll put a card to lesson 4 here. This week, we're going to talk about two specific types of relation: functions and equivalence relations. We're going to do functions first, but I would definitely stick around for the second half about equivalence relations because it is a super fun and interesting concept. So what is a function? It's actually pretty simple. A function is a relation where for every x or input in the domain, there's exactly one y or output that x corresponds to. In our relation notation from last week, we might say, for each x in the domain, there is exactly one ordered pair xy in the function f. You've probably already learned one way to check if a relation is a function, the vertical line test. Say we have some relation r between x and y on the coordinate plane. If we can draw a vertical line that passes through more than one point, then there exists some x, the x-coordinate of the vertical line, for which more than one xy is in R, so R can't be a function. In set theory, we expand this to encompass relations between any types of x and y, not just numbers. Let's say we want to relate the set of positive integers and a set of 10,000 people. So we define the relation R equals the set of ordered pairs xy, such that x is a positive integer and y is a person whose name has x letters in it. For x equals 5, for example, there are probably a whole bunch of people in the set with names that have 5 letters. So R is not a function. But what if we flipped R? Let's say S is a set of ordered pairs xy such that x is a person and y is the number of letters in the person x's name. Well, a single person can't have multiple lengths of their name, it's a fixed value. So S is a function. Each person x corresponds to one and only one name length y. We call this property well-definedness, and relations with this property are well-defined functions. There's no such thing as a non-well-defined function, but a relation is a function if it is well-defined. Functions are super important in all kinds of math and science. Pretty much all normal math, algebra, calculus, etc. is based on functions. Statistics and computer science also rely heavily on functions. That's because of this well-definedness property. In a computer program, you never want to have a situation where you tell the computer to do something with a certain input and it has multiple options for what it could do. The same goes for statistics. Given a certain value for the x-axis, or the independent variable, you want to be able to predict a single outcome for the dependent variable. So you can see how well-defined functions allow us to create a sense of direction or time. Relations just connected two sets A and B, but with functions we can translate things from A to B. We're going to quickly learn about 4 definitions involving functions. First is the inverse of f, written as f to the negative 1 power. The inverse of f is the set f inverse equals the set of ordered pairs xy such that f of y equals x. We just flipped x and y. You could also imagine that if we're traveling down a road, f, to get from x to y, the function f inverse is the same road but traveling in the opposite direction. Second, the composition of f and g, written as f circle g, or fog, is defined as the set of ordered pairs xz, for which there exists some y in the domain of f, such that g of x equals y and f of y equals z. A more common way of saying this is f circle g of x is equal to f of g of x. For example, let's say that we have a function g mapping from the set A to the set B. That is, g takes in elements of A and puts out elements of B. Now, let f be a function mapping from the set B to the set C, where f's members are ordered pairs yz, with y in B again, and z is now in C. Then the function f circle g is a function mapping from A to C, first hopping from A to B on G, then hopping from B to C on F. Next, the restriction of F to A is a set. F half upward arrow A is equal to the set of ordered pairs xy such that f of x equals y and x is in A. Once again, imagine some function f from B to C. A is some set that intersects with B. The restriction of f to A is the set of xy in F where x is not only in B but also in A. It's a greater restriction on the members of F. And finally, the image of A under F is the set F double bracket A equals the set of all Y for which there exists some X in A, such that F of X equals Y. It's everything that you can get in the range of F that was sent over there by an element of A. This is also equal to the range of F restricted to A. There are a whole bunch of examples and theorems involving functions. I'm going to skip over most of them because they're on a more micro scale than this video series covers, but I will try to find a video that talks about a few of them and I will link it in the description. The second topic to cover in this video is equivalence relations. Equivalence relations are also super important because, as we'll see, they let us group things together in a way that's more defined and usable than just putting things into discrete sets. The best example of an equivalence relation is the equal sign for numbers, simply saying that two numbers are equal to one another. Using the equal sign, we can say 1 equals 1.0 equals 5 over 5 equals the derivative of x equals the number of suns in the solar system, etc. We say that all these different ways of expressing one are in the same equivalence class, which we write like this. The equivalence class of everything equal to the number 1 by the equivalence relation equals, or bracket 1 sub equals. Or bracket 1 sub equals. But equals isn't the only equivalence relation. In fact, instead of equals, we could use any relation R that satisfies the following three conditions. First, R is reflexive, meaning that for all x, the ordered pair xx is in R. That makes sense because we want everything to equal itself. Second, R is symmetric, meaning that for all x and y, if xy is in R, then yx must also be in R. If x equals y, y should also equal x. And lastly, R is transitive, meaning that for all x, y, and z, if xy is in R and yz is in R, then xz is in R. So if x equals y and y equals z, then x equals z. Another way to say xy is in R is simply xry. We can think of R as standing in place of the equal sign, so x equals y is the same as xry. In that case, a formal definition of the equivalence class of x by the relation R would be bracket x sub R equals the set of all y such that x are y, or using equals, the set of all y such that x equals y. Basically, it's the set of everything that is equivalent to x according to whatever equivalence relation we've decided to define. Another useful example of equivalence classes is the example of modular arithmetic. If you're not familiar with modular arithmetic, I'll also find a link to a video about that and paste it in the description. But basically, modular arithmetic is a topic in number theory where we pick a certain modulo or mod and group numbers based on the remainder when divided by that mod. So for example, 7 mod 6 is the same as 1 mod 6, is the same as 13 mod 6, and so on. All the remainders are 1. We can express these groups as equivalence classes on the relation defined as xry if and only if x mod 6 is equal to y mod 6. That is the remainder of x when divided by 6 is equal to the remainder of y when divided by 6. So the equivalence class we just described would be bracket 1 sub R, the equivalence class of everything equal to 1 mod R. In fact, sometimes in set theory, we'll use this modulo language to describe any equivalence class, not just this one. Bracket x sub R can be said as x mod R regardless of what x and R are. One way to visualize equivalence classes is through something called partitions. Let this blob be the set of all positive integers, which we will denote n for natural numbers. Now, we can partition this blob into 6 classes based on the values mod 6. The first class would have 1, 7, 13, etc. The second one would have 2, 8, 14, and so on until we get to 6, 12, 18. And now we put every single positive integer into one of these 6 equivalence classes, which are themselves subsets of n. The partition, which we write as capital Pi, is the set of all 6 of these subsets. The subsets in the partition must be disjoint and exhaustive, which just means that they can't overlap, but together they have to cover all of the domain set n. There can't be any numbers that isn't in any of the equivalence classes. This partition thing reveals one reason why equivalence classes are so useful. The set n is an infinite set, and while it's a relatively well-behaved set, the The set N is an infinite set, and while it's a relatively well-behaved set, it's so much easier to look at the partition of N mod 6, which only has 6 elements in it, the 6 equivalence classes that we've equated to 1, 2, 3, 4, 5, and 6. An example of a domain set that's less well-behaved is the set of all expressions with a numerical value. Remember at the beginning of the video when we said 1 equals 1.0 equals 5 over 5 equals the derivative of x equals the number of suns in the solar system, and so on? This is a horrible, horrible set to work with. It includes integers, decimals, fractions, and then a bunch of weird arbitrary stuff like the number of grains of sand on Earth in the year 1400. I don't even know what to do with this set. But by partitioning it into the equivalence classes 1, 2.5, pi, 8000, etc., we have condensed this crazy set into something that we can handle, aka the number line. This partition is actually uncountably infinite, but it's still way better for math purposes than whatever we had before. And that concludes the 5th video of this video series about set theory. I hope you enjoyed it. Let me know what you think, and if there's anything that would make it better. Also, make sure to check out the example problems in the description. Thanks for watching. See you next week.